This is Dr. Aidan Bharath. He's going to be giving this talk today. He is a research and testing engineer at the National Renewable Energy Lab. His work primarily focuses on bespoke data acquisition system design for offshore ocean renewable energy technologies. His collaboration with the University of New Hampshire has developed a novel system which is capable of capturing blade strain measurements from an operational turbine in real time and correlated to several other measurements being captured on the Living Bridge platform. Aidan's background includes several aspects of the ocean renewable energy industry, including modeling regional scale tidal resources, reporting on water commercial deployments, extensive tank testing campaigns, wave energy converter arrays, and building high fidelity CFD modeling techniques to wave energy and tidal energy converters. Everyone, Dr. Aidan Bharath.
Thanks for having me. So today I'm going to try to do a very broad talk about research activities in the green energy space are at NREL. So besides all of the stuff that I'm doing, particularly with the University of New Hampshire and through a lot of the other projects that I have, I'm going to try to speak to a lot of other people's work. Feel free to ask me questions really at any point, but sometimes I might not be able to answer those directly. But I can absolutely point you to the person who can. Just wanted to say that right off the bat. A little bit about me. My intro was kind of written at about 12 a.m. maybe 2 days ago or something like that. So it actually did a pretty good job of what my background really is. But for the most part, a lot of my big interests are on open water deployment and data acquisition systems. So a lot of the projects that I am doing at NREL that I primarily focus on are expanding our capabilities with our MODEX systems for open water deployments. And really focusing on doing the testing and gathering data in really difficult situations. Those really get me going. This is one picture that we took maybe last week of us trying to install, a pretty interesting system on the Living Bridge platform vertical axis turbine, which is currently up and running, and I'll be talking about that later. You can see that I'm doing pretty fun work, basically like just taking pictures of everything that we're doing, just to promote it. So what is NREL's interest in the ocean? So to my understanding and to my approximation, what NREL is really trying to do is assist with a lot of fundamental research to help companies build toward utilizing the ocean resource in a very sustainable and very, profitable and commercially viable way. As you probably know, 40% of the global population lives really right next to the water because it's just better in most cases. There's been a lot of work put into the estimated potential of the blue economy, so industries in the ocean, which can have been told to go up to about 3 trillion by 2030, which is a massive number. What NREL is really trying to do is to try and help that get to where it needs to be. So through a lot of some of the work that I've been helping out with at NREL, we've really tried to quantify a lot of what the technical ocean energy resource is in U.S. coastal waters. And really when you try to add everything up, including wave power, tidal power, ocean current, and OTEC, you can get up to 2,300 or couple thousand terawatt hours of power, which can come directly out of the ocean, which is massive and will make a huge dent in the fossil fuels that we use currently, if we are able to capture that. Getting a little bit more into what NREL is focusing on is really looking at integrating new and novel marine hydrokinetic technologies into possible commercial uses. So getting into a lot of the PBE aspects, which DOE is really trying to build up at this point. And also there's a lot of focus on, sorry, I just saw it click to add text in the middle there. There's a lot of other spaces in terms of decarbonizing the world. So being able to make hydrogen, methanol, ethanol fuels, and ammonias using these power technologies is something that's been really thought of as a good use case. We're starting to put a lot of effort into looking at that, and also the transition to being able to power certain subsea data centers, and really building the use case for all of those alternative fuels. Yeah, that's a major focus of what we were trying to do. So yeah, on a broad scale, one of the things that NREL as a whole would really like to push forward to see is, of course, utility scale electricity generation from ocean renewables. As I said, we sort of tend to work mainly on wave and tidal, which are some of the most promising ones at this point. But also that decarbonization aspect. So being able to develop or use these energy sources to create alternative fuels would be a big step in decarbonizing a lot of the shipping industry. Again, pushing into the blue economy, you know, if there's other bespoke or unique use cases for a lot of these power systems, so that gets like aquaculture, you know, ocean observing, having buoys powered in the middle of the ocean for long periods of times. Those are all things that we can use these technologies for. And also some of the other aspects that we're really trying to get into are looking for equitable energy transitions, which is, I mean, kind of the way I understand it, really making sure that, you know, nobody is left behind in some ways. So getting smaller communities involved in a lot of these projects, because in some of the cases, if you look at somebody who's in the middle of nowhere, Alaska, with a nice tidal resource beside them, they pay a lot for diesel to power their homes right now. So they would be an early and direct benefactor from some of these things. So that's something that we do have a lot of people working on, trying to make all of that happen. But yeah, and climate change mitigation, that's sort of the umbrella topic. We gotta stop burning so many things. But yeah, there's also a lot of opportunity across multiple scales. So as we move forward and this technology becomes more and more mature, we have a few, you know, targets that we're trying to hit, which I'm sure are backed up by a lot of government entities and government targets and things like that, which are going from small, you know, few 100-watt scale devices, which we've had a few interesting successful deployments on, but moving up to kilowatt devices, which are, you know, powering small communities and powering a lot of the blue economy type things, up to, you know, megawatt and gigawatt scale projects, which are be amazing to see once it happens. But it's also what it does say plus years there. It's a little way away. I went backwards. No. That's a different slide. Okay. Okay, so yeah. So at NREL, again, some of our priorities are really to support some of the testing facilities, AMAC being one of them that's just started up, but also PacWave on the West Coast, connected with OSU for wave energy, primarily for wave energy testing. And of course, supporting a lot of pilot projects with anything using our resources, anything that we can help on there, we're more than willing to do. But also pushing forward a lot of the blue economy initiatives, doing a lot of technology validation, either using modeling or using our testing facilities. And also we have quite a large group into fundamental R&D and innovation. And yeah, we have quite a number of tools in terms of high performance computing to run a lot of these fun models and develop new models, and also are very much involved in gathering a lot of data and really pushing it forward into AI so that we can hopefully provide the data needed for people to get started to understand the ocean in a much better way. But yeah, so at NREL, again, I don't remember this probably a little bit at this point, but we do a lot of modeling and analysis, innovation and design. So we have some really cool sort of flexible material lessons and sort of out there ideas that we're trying to flesh out. We are currently building up a lot of our laboratory validation specifically for wave energy testing. But in combination with what we're doing at UNH, we do a lot of open water demonstrations, help out with pilot deployments, and one of the big things that I'm going to talk about later in this presentation, hopefully if we have time, is workforce development. because to drive this forward, we really need people to do the work. I can't do everything, unfortunately. But yeah, so one of the projects that I am pretty heavily involved in is what we call our Marine Energy Atlas, which is an open source tool, which is hosted and managed by NREL, which is meant to be a large scale data repository, which currently is hosting some of the most high resolution wave hindcast data sets, which span over 42 years, which go down to about 200-meter resolution near the coast and cover a large portion of the US EEZ waters, which is something that's huge. This is 50 to potentially 100 terabytes worth of data. We can't really expect somebody to get that whole thing and plug away at it. So we developed this whole online tool to be able to promote it and let users be able to access it in a nice timely fashion. And we're slowly building forward on this, and we're implementing tools so we could start to calculate capacity factors, anything to really do with joint probability distributions and starting to get into some statistics. Yeah, we're building a lot of that functionality in there and also tying it with the primer project. There's going to be some pretty interesting things happening with the Atlas in the upcoming years. On the side of making all of these new technologies actually economically feasible, we do an extensive amount of work in technical economic analysis. So we have the SAM tool, which stands for the System Advisory Model, which, as far as I understand it, when you're working with particularly wave energy, you can, even in combination with the data on the Marine Energy Atlas, you can take the performance of the device, align it with the data from a specific location, and you can get some interesting numbers on actually if your device will be capable of being profitable in a certain location. There's a lot of interesting things that can happen there, but really focuses on promoting system design or developing system design, system performance, and really just going over the initial project economics and things like that. And it's always something that's ongoing and being developed as the industry needs it. So it's a pretty cool tool. On the modeling and analysis side, we do have, as I said, a lot of HPC resources. So there is a lot of CFD work that's going on at NREL, but we also have the tools for wave energy, which is WEXIM, and also OpenFast, which are, not CFD codes, but parameterized codes in some way to really look at time domain performance of tidal turbines and wave energy converters, which is something I'm loosely involved in. But more so, I'm very much interested on the WEXIM side to actually bring in a lot of control aspects into that, do novel control systems. But yeah, there's definitely a lot of work there. Quite a few were very involved in Teamer, especially on the modeling side. Quite a few projects that are happening. Even one that I think it was RFTS 6. We started a collaboration with Lancaster University to work with their Talos wave energy converter device, which is a pretty interesting device that has a inertial mass within a hull that's capable of actually collecting energy from all 6 degrees freedom of motion, based on a pretty elaborate hydraulic power takeoff system that we're hopefully going to get working in WEXIM pretty soon. I'm excited for that one. That's pretty cool. But yeah, on the OpenFast side, there's been quite a lot of effort being put into taking the wind side OpenFast models and being able to apply it to ocean turbines. So that means adding a lot of expanded models to account for cavitation, buoyancy, the added mass of the extra weight of the water hitting this, the inertial loads, and of course, I believe Hannah Ross is working on some wave current models as well, which is pretty cool. And especially in combination with the vertical axis turbine here on the Living Bridge, we're hoping to really develop models that really accurately or improve the accuracy of models that can model those types of turbines. Right. So this is Wexen. So we went into this a little bit, but it's a again time domain solver of wave energy converters that's uses MATLAB and Simulink. It's something that has been developed and it's under current development for the last couple of years, last quite a few years, and it is being used really successfully in a lot of teamer projects, some that I'm heavily involved in, and quite a few others. Has been used for flexible material or FlexWEC projects, and some really interesting things, but can account for mooring systems, structural dynamics, system dynamics, fluid dynamics, and power system and control systems, which is something I'm pretty interested in. Right, so getting on to the innovation and design, this is where a few of our teams can really just go crazy. So with some of our flexible WEC technology, we have some interesting design which we're using. I think they're called elastomopolymers or elastopolymers, which basically is a solid structure, flexible structure, which has its power conversion units effectively embedded into the flexible membrane. So if I'm understanding this picture correctly, here you would have a solid mass within a solid hull, which is connected to the connection between the two surfaces is that elastopolymer stuff. And as those two things move in reference to each other, basically you're generating a current. And there's a huge amount of benefits to this because you don't have anything really solid. So you reduce reduce a lot of the fatigue loading, you can extend a lot of the life. A lot of these materials can be significantly cheaper once you get to manufacturing scale. And I think there's a lot of promise in these types of things. And another huge benefit is that you can make them into a lot of different shapes. So you can have devices like this, you can have little like snake devices, something like that. This guy's the limit. And it's pretty neat research. But and also one of the large projects that we have, I think it's finished, down in North Carolina was deploying the waves to water wave desalination NREL buoy, which operated pretty successfully, as far as I know. I was pretty involved with some interesting data acquisition systems bolted onto the side of these, which some survived, some didn't, but it was definitely exposed to some of the worst conditions that the ocean can really throw at it. So it did good, and hopefully I can talk about that a little bit more later. So getting into more of what our laboratory testing capabilities are. At our satellite campus, the Flatirons campus, which is just south of Boulder, Colorado, we currently can do quite a bit when it comes down to structural testing and PTO dynamics testing. So with our dynos, we have a 25 megawatt dyno, which is pretty big. We were originally a wind testing site, so we are able to do fatigue loading or fatigue loads on wind blades, which are way bigger than anything that we see in tidal. So we have a lot of capability built up to do structural and fatigue testing there. We're continually updating our resources in advanced manufacturing. I know Casey Nichols, who I work with quite a lot, is very excited to get robots online. It's going to be pretty neat. One thing I'm really interested in is our large amplitude motion platform, or they call it LAMP. That is meant to really be able to take large, not full scale, but sort of large scale WECs, take them out of any type of tank testing, but still be able to subject them to real wave loading. So it's a 6 degree of freedom motion platform, which we can subject a lot of loads to scale models without having the possibility or the added cost of having to set these or build these data acquisition systems or testing systems to be able to operate for long term in water, which, as you can imagine, can get pretty expensive. But also, I mean, on the other side of that, we have recently set up our own small scale, I think 100 scale wave tank testing basin, which, I mean, some of my ideas for this are to really advance sort of rapid prototyping small scale devices with a lot in combination with our advanced manufacturing and things like that. But yeah, there's a lot that we can do. So yeah, I mean, more on the data acquisition side of things, we have, our team, which works with CPower, Virginia Tech, Verdant Power, and our MODAC data acquisition team, which I'm a part of. Yeah, we build a lot of bespoke systems. We put them out into the field. And we definitely have a lot of capability to go out there and fix things on the fly and really be available to cater to the needs of the client, which is something that we're still building on, still working on, and but we're learning a lot and bringing it to every new project that we start. Yeah. So some of the open water demonstration products that we have done so far are, like I said, the waves to water desalination WEC project, the ocean energy buoy, which I believe is still sitting in Hawaii. We work quite heavily with the University of Hawaii WETS, sorry. And also some turbine developers like UNH and Verdant Power. And also on the resource assessment side of things, which I mean, that's kind of my bread and butter. We have worked a lot in the Cook Inlet to really develop a lot of the high resolution turbulence analysis of the East Forelands test site, which has been pretty awesome. But we've also been looking at a lot of the smaller, more hidden tidal areas there as well. And yeah, are looking for ways to get a better understanding of what the resource is there. It's it's very far away and kind of expensive and cold to get there at certain times. But yeah, that's really what we like to do, or what I like to do anyway. But yeah, so getting a little bit more on topic for what we are doing in combination with UNH at the moment. We are using our MODAC system, which is a modular ocean data acquisition system, which is something that we built on National Instruments hardware currently. But we built it in such a way that it's all open source. I believe you can go online right now and get all of the code that we've ever written for it, or a large portion of the code that we've written for it. But yeah, it allows us to make a lot of bespoke systems that we have launched onto the OE buoy, or launched onto the UNH platform, tuned it to whatever, basically, in this case for UNH, whatever the students need for their work. We've been able to provide, well, one of the reasons why I'm here, on-site support, which is always nice. But yeah, we also develop systems that always adhere to the IEC standards and the ISO standards requirements for that. So we have a lot of confidence, and we have a lot of background testing in how the data will come off the systems, provided it works properly. If something breaks, who knows what will really happen. But yeah, we can do power performance testing. We're accredited for power performance testing. We can do mechanical loads, health and system monitoring, condition monitoring, real-time data streaming, which is near real-time data streaming. We could set up SCADA systems. We can do alerts. We can do feedback control and things like that with MODAC. Data quality, intelligent data management, which is a big thing. And also everything with our systems, we try to have everything timestamped, because as you can imagine, with very separated systems, you have clock drift, and that can lead to a grad student having a lot of heartaches in the future. So we try to avoid that. And so far, so good. But yeah, this goes into a little bit more of that. We have MODAC, that nice stuff, goes to MODAC Cloud. This is where you have a lot of the that high-level data processing and data storage side of stuff. Usually, as soon as something goes into the cloud, it's backed up in a lot of ways that you can't really lose it. But also, one of the things that we are working on at the moment and are piloting in this collaboration with UNH is what they call the MHKit data pipeline, which will take that data that goes up into the cloud and automatically run it through QC analysis, which is something that would be huge, because now instead of focusing 8 hours a day on running a test and going home and doing another 8 hours of data analysis, I'm really pushing for some sort of report that can just be automatically sent to you, which would be amazing. Save me a lot of time. But yeah, so let's dive into field testing at the Living Bridge platform. So I'm sure a lot of you have seen this system before. It is a vertical axis turbine developed by a Canadian company called New Energy. It's been on the platform now for, I believe, 3 years, and has been actively used. We started working on this project with UNH, I believe, in 2021. So this would be coming up on the end of the second year of our collaboration working on this turbine. In our first year, we were successfully able to really update the MODAC system and bring it up to right. What was I saying now? Yeah, basically revitalize the MODAC system and continue to actually gather data off of this, which is which was quite successful. We're always doing it in an open source way, so all of that data is available. But yeah, continuing. Oh, did I break it? There you go. I tried. Perfect. Yeah, continuing on to this year, because in some sense I thought it would be pretty simple. We decided to expand our data acquisition system from being able to correlate inflow to turbine thrust and PQO power output, which we were collecting in our first year, to basically add correlated blade strain measurements, which of course, that's how difficult is that? So eventually what we did is build a dual bearing system, because this is taking data that's collected from a submerged rotating frame. Was way out of scope to be able to get some sort of slip ring that can survive that type of system. And if we were to use Wi-Fi, which was the solution that we used, Wi-Fi does not work too well underwater, so we had to get those transceivers above the surface. And because this is a tidal turbine, the blades are under the water. So what we ended up designing was, basically something that will rotate with the blades, bring the data up out of the water. And because we go through pretty extensive design reviews on all of the systems that we do build, one of the things that we added to this was a outer fairing that aligns with the flow and allows the data acquisition system to rotate underneath it. We added one of those just so we could quantify what the actual loading on the system would be. Because you can imagine, without that, then you have essentially 2 more blades spinning, not quite at the same radius, but still spinning, when we have a very vital data cable in there as well. So that fairing solved 2 issues solved quite a few issues, but allowed us to know the loads, protected the cable, and made sure that we didn't have any weird effects that we really couldn't account for. But also, we had Martin and UNH send us one of their blades and 2 of their struts. And we sent this out to be machined and put 8 full bridge strain gauges on it, recoated them with a nice little epoxy, sanded it all down. So we have basically an instrumented blade with roughly the same profile, or pretty close to the same profile as a completely new blade. And again, did all of the FEA analysis on the changes that we are making, and gave them back basically a system that was intended to just be bolt on. It took a few more bolts, but we got it to work. And yeah, as you can see, this is actually Patrick. was working for Martin at the start of this and now works for NREL. But yeah, it's something that we were able to come down to UNH, and as the turbine was still just on the platform, but at the UNH pier, we were able to install this full system, start testing, and yeah, to say that that so far everything is going quite well, and we're starting to see data coming off this system, which is very encouraging. A lot of this, but yeah, so I mean, as you can see, these are the underlying bearings, these two pieces here. The blue drive shaft, or I guess bearing housing in this case, does not move. So that's just stationary. The blades obviously move, so that's basically the need for those bearings there. This is the sunken cable routing coming off of the blades, which would probably be here in this case. That comes out of the blades. This is sort of a custom-made armored and stiffened cable that we developed in-house. Developed a system for that to run up under the outer fairing bearings, straight up to where the data acquisition boxes will eventually be. So you can see that's us installing this here, runs up the back on the trailing edge of the rotation. And yeah, we've secured it down quite well. Yeah, I could talk about that for hours. I'll probably just start rambling. So, but yeah, so we did get this all together, and we got the platform back under the Memorial Bridge, and you can see fully assembled, ready to drop at this point. The fairing is on, everything is secured, and basically banded, sealed, and ready to deploy in that case. So, and the way we've rigged it up is really, we just hit go on MODAC, drop this into the water, and we're collecting data, sending it to the cloud, getting everything going, getting everything moving. And it's been a journey, but it's working out pretty well. I'm pretty happy about it. Right, so actually before we get away from that, I did have a video. I can make that work. This thing actually operating. So. So as you can see, the drive shaft completely stable. The turbine under is operating and generating power right now. Yeah, it's very excited, so forgive me if I say something bad. But yeah, in this case, again, the fairing is aligning itself with the flow and everything. The struts and the cable are rotating under that, under the bearings that we did make. As soon as I get back to it. This is during, I think, the trailing edge of an ebb tide. The trailing end of an ebb tide. But yeah, even though it was getting splashed with water, we sort of expected, or we were hoping there wouldn't be any issue with the Wi-Fi because those transceivers are in those boxes. But so far we haven't had any issue, which is very surprising to us. But yeah, we're collecting data at 60 hertz. But we're also keeping track of the rotation of the turbine, which is definitely an addition to what the data acquisition system was before. And I think yeah, it was pretty interesting. So yeah, overall, we're all so far well. And combined with all the measurements that we have made before, we are hoping to run this in a very attended mode to continue data collection for hopefully the length of the spring and neap tidal cycle. There we go. And we are planning to do that in attended mode because, as you can see with the water where it is on these boxes, it's pretty much bad if if anything really substantial hits those, or I mean, that's one of those big unknowns with working in the water. Hopefully something doesn't hit them. They should last for a long time if nothing hits them, but anything can happen. So to ensure that we have enough data to really provide to our modelers that they can do some good work moving on, we're going to have probably some undergrads or something like that stand out there in the cold and make sure sticks don't hit it for a little while. Yeah. We're gonna do that. Sorry, how do we keep going? All right. So talking about undergrads and interns and things like that. Yeah, it worked out well. Yeah, so one of the things that we do, or the Office of Science allows for us to do, and forgive me, I don't know these programs too well, but our SULI program does give undergraduate students who would like to get experience working in lab projects and things like that, the opportunity to do that. I've used a lot of SULI interns. They're pretty heavily used within the water power office at NREL. And it's definitely a good program. You should go and apply. It's always nice. And then there's visiting faculty programs, which again basically provides a source of funding for either visiting researchers or visiting graduate students to be able to get funding to go and work at the labs, use lab facilities, and get exposure to what we're doing. The MHK Graduate Student Research Program, which is basically another platform for that. So as I understand it, once you're into that higher level graduate research, you can get a bulk of funding again to go and work at the labs, but also get a little bit of funding to actually help your research, which is also quite nice. Monthly stipend, and they also pay for school, which is also a pretty big benefit. So apply for that, December 2nd, deadline for this year. Okay, so again, a few other programs like the GEM program does a lot of the same thing, provides a stipends and allows visiting researchers to come and use lab facilities, pays for tuition, gives you a little bit of a stipend, and it's definitely something that you should look to do. Even more opportunities. So there's actually, I think what should come out of this is that there's a lot of opportunity to, as a student, be able to get involved on the lab side of things, which will, provide funding for school and give you a lot of opportunity for exposure to continue on with your career. AMAC. What am I supposed to say about AMAC internship. Sorry, it was blind. Now I got it. But yes, this is one thing that we have been trying to stand up in the last little while, where through our partnerships with AMAC, that we are trying to at least once a year be able to bring on a student intern to work on some of the collaborative projects that we have going on with the AMAC facility as a whole. So this could potentially be very interesting, could expose students to a wide range of very interesting projects, which can combine work at what NREL is doing with UNH, Lehigh, Stony Brook, and CSI in North Carolina as well. So it's pretty interesting opportunity. That seems to be it. So I guess questions along with
your data acquisition system, I assume it's battery powered. You might have said I didn't.
It can be. We can.
The one on the pole.
The one on the pole is, yes.
What do you think the endurance will be at that?
We are anticipating, because right now it's actually powered, even though it's not operating and collecting data. Because those boxes have been siliconed and sealed, we just left it powered. But in sleep mode, we anticipate that those batteries will actually last 6 weeks to 8 weeks, depending on the temperature and things like that. But in operating mode, it's going to use more power, but we still assume that, or estimate that it will go for about 3.5 weeks to a month, continually operating. But of course they are rechargeable if we run out of power, and we could see how much power we have through some Bluetooth systems that we have. We're thinking once we get down to about 20%, which is when our voltage is getting a little bit low, we're going to take the time, we're going to open those boxes, get everything charged, and refresh the system. But because there are so many seals and things in place, it's not something we want to do often.
You duty cycle the system to capture parts of the tidal cycle that are interesting and extend that endurance?
Can we extend that endurance? Yeah.
I mean, like, power down the system during parts of the tidal cycle for which interesting measurements wouldn't occur. You know,
Yeah, we can put it into sleep mode. So we're not actively collecting data, which is, as soon as you stop the system, that's what it does. So that's where you have effectively no power draw. I think that system has been running for about 2 weeks now, and it's still reading 99% state of charge. Still almost don't believe, but that's what it's telling me.
So your fairing bearings, what are they made of, and how long do you expect?
They're Durham. And again, during our design review, they're Durham bearings that we bought the material from DuPont, who gave us quite a lot of paperwork on what once you build these bearings, how long they'll last. And we're well within the range. We're not spinning anywhere close enough to really fatigue these materials at all. The issue that we did come up with is a lot of this testing and a lot of these numbers were quoted for laboratory conditions in air. So there's a lot of unknowns in that one. The biggest thing that'll hurt us is if something gets in there, but we do have pretty tight tolerances. But yeah, that's one of the big outcomes from this is have those bearings survive, especially because they're going through wet, dry, and probably cold temperatures at this point. There's no like properly closed area in this, so we're not too concerned about freezing as soon as things get really cold and it's sitting out of the water. But yeah, it's something we're interested to see how it lasts.
Yeah, so every system you're building is unique. What are some of the biggest challenges you faced over the years with trying to instrument marine energy systems?
There's a huge amount of challenge. One of the biggest ones for long-term underwater deployments is corrosion. Because water will get everywhere, and especially when you're trying to say look at the loads on a mooring system or something like that, and you can't run a cable all the way to shore or anything like that. You're going to have a little battery powered system connected to those cables. Anything happens to those cables, they're going to corrode very quickly, and you might not know about it for a long time, which is something that's always been a challenge. So basically having something that's robust enough to really survive. And also one of the biggest things that we really are working on right now is just having the procedures in place to be able to bring all of the team together. Maybe there might be divers who are hired from somewhere, or electrical engineering teams that you only have one specific job for, but they may interact with our systems. Being able to really coordinate with everybody so that everything works how it's supposed to and nobody interferes with things, that's a big challenge. Especially the larger the team gets, the more difficult this all becomes. So, yeah. That answers your question.
So every system that you make is unique. Is that because you are looking at tailoring each system to specific environments? Is there?
Yes, and also because in the space there hasn't been, at least from what I've seen, too much conversion on what the technology actually looks like. So we're dealing with a lot of unique devices. So this new energy turbine, which is on the platform, it's not. There's been quite a few of them built, but again, we are just looking to extend the research life of this device. So it's not a turbine that was built to have this kind of data acquisition system on it. But we have the opportunity to do something like this. So we're okay, let's make it work without modifying it too much. But then you get new designs like the OE buoy, which is an oscillating water column. That has an entirely different set of parameters that we want to collect data for. It requires a different system. And yeah, it really comes down to that, where because we're a national lab, we're not really, we're not for profit. So we're not looking to design a system that's going to be sold, built millions of times over. We are looking for those unique development projects, build something to help those companies get to the next stage of development. That's what we're looking to do. So that almost just requires new and bespoke systems every time, which is fun.
You mentioned the tidal resource measurements in Cook Inlet, and I was curious if you could talk a little bit more about how you collected those observations and what you were specifically interested in, whether it was like mean current or more of the variability to make those.
We used our Stablemore buoy system, which is, you're shaking your head. Are you familiar with that one? Okay, that's so we had an upward facing ADCP and downward facing ADCP on this with an ADV right on the nose of that. I believe we had it, if I remember correctly, for most of those measurements, we were mid water column for our deployment site in the East Forelands, which I believe it's about 60 meters. So I think it was hovering between 20 and 30 over its measurement period. I believe from the ADCPs, we did have about 2 months worth of data coming off that, which is pretty good. I don't know if it's the same for the ADV, because that uses quite a significant more battery power. But yeah, that's all data that we should have available or soon have available.
So I'm assuming the ADCPs helped refine the mean flow and the ADV was more turbulence.
Exactly. Yep. And it's also, we go a little bit, I believe there were I think a turbidity sensor on there and a few other things. I know one of them got unfortunately ripped off. And it's just somewhere in the Pacific at this point. But if you want to if you want to know more about that data set and find it useful, feel free to reach out.
Okay, great, thanks.